Start recording. Okay. So last time we left off, we'd found out the potential separation axes and their overlaps for our two shapes. And if you can just look at this diagram and you'd be like, well, this is the shortest of these 6 arrows, so this is going to be what we're going to separate with. So what we have to do is go through and find the shortest arrow and search for it, and then use that to separate. And you'll notice we have these arrows all pointing in the right direction, so they're the amount we'd have to move the rectangle if we moved it on that axis. So I did want to take a little hop, skip, and a jump over to the this code, because I thought, seeing as we're relating this back to the River City Ransom engine and Pixel 3D. Are you familiar with sort of the pattern that's I'll probably write this on the whiteboard. It's like int best index var, probably not var, but whatever, best foo, and then you go like for I equals 0 to whatever, if foo I is better than best foo, foo, and then we save out, best index equals I and best foo equals foo I. Like, that should be pretty familiar pattern, yes?
Yeah, for sure.
Yeah. So, if that's particularly familiar, there's not too much interesting to look at in the repository.
I'm actually totally mesmerized by the idea that there's only one commit in that. How is that possible?
What?
I've been committing to that all day, every day, forever.
Am I on like a branch or something? Oh no, I'm on a wrong revision.
I got
there we
tooled
go.
by my own. Okay, there it is.
Yeah, because I pulled this back up from the other thing. Okay.
Oh,
so
maybe you were trying to read it from how it looked like the first day, maybe.
No, I had this up and then I'm like, and this one hasn't changed since the first commit, and so then I went back to the top repository and it's like, yeah, well, you want everything from that particular commit.
Gotcha.
So if you search this repository for best, you basically get all of the instances in the code just about where that is taking place. Best distance squared, best index, there's exactly what you have there.
And this is like the SOA stuff, right?
Well, this is anything. Like some of these some of these, definitely are SOA style. There's actually not as many as I thought. There's only 1 page worth of these. Like you can see these ones obviously, are SOA. So I thought, seeing as we're doing this pattern, it might be interesting to look at some of them in the code base. And there's this interesting one in Image Writer, which is, it's there, and we don't need to go into it in too much detail because it's pretty obvious. But where did it go? Yeah, so this pack function, it's looking for the best location to place the images when we pack the images, and it goes through and it's a greedy search, so it's searching exhaustively for the best one. And so that's what we're going to be doing. So we have a very similar thing here. So we have we already have the equivalent of found, and in this case it's like it's like did intersect is our found, and so we're going to add we're going to try and find the best axis and what distance on that axis. So let's get rid of that now. And
so
yes?
best is obviously entirely dependent on the fitness function. In this case, when you say best, you mean the minimum distance?
Exactly. So we've basically already got this code. So we can scroll up to so we're already doing a little bit of that here. We're picking the best of the two possible separation directions. So this is what we already copied down, if you remember from last time.
Mm-hmm.
And then down here, because we only have two axes for the rectangle case, we're just doing a straight up comparison and choosing the best one. But now we have 6 axes, so we basically have to do this same thing for all 6 axes. So let us, we probably don't need to copy this, but just observe what's here. We've got N, which is the axis direction, and we've got separation, which is the amount on that axis. And we're finding the best separation, and then we're copying out the best one. So we're going to do exactly the same thing down here. So let's see. We need. I'll tell you what I need is I need my notes up. So where's my loop? Okay, here's my loop. So we've got did intersect. So we need the vector2 separation axis, and we need a floating point separation amount. Now
we're doing this all in the drawing code. Is this the time to not do that, or is this we gotta wait for that time? Because we won't be able to. We're not gonna call the separation function from the drawing code, right?
No. So this is just so we can draw out the separation. So we're still searching within these 6 axes on these two shapes. So when we copy this out, all we need to do is basically get rid of all the drawers and loop over it. So the separation amount, we want to find the smallest one. So what we do here is well, exactly what you're doing. I tend to go for float.infinity, but
Ooh, that's even better.
yeah, I'm not sure I've thought. Sorry?
I'm just curious. Want to know what it doesn't actually say what the constant is for that.
Yes. Well, we could have a grand old time talking about the floating point IEEE format and how the different values are represented. It's actually really interesting. So maybe not today, because I'd have to actually go and re-familiarize myself, because I was about to say I used to know the various trade-offs for these things, and now I completely forget. But maybe another time we could have a talk about that, because it's actually interesting.
I thought float was pretty much like game disease because of endianness and floating point issues on different machines for networking and so on.
Not really. That's kind of an issue specific to River City, because I guess it's not just River City. It's any game that wants to have. Oh, there's a technical term for it. It's not reproducible. It's
Deterministic.
Deterministic. That's the one. Yeah, any game that wants deterministic playback of a series of events. Pretty much either you can't use floating point, or you have to have pretty much the same compiled code, the same compiler, but hope the compiler doesn't change what optimizations it does for whatever reason. So same compiler, same CPU settings, if not the same CPU. And
that's all just because like you can't replay the event and guarantee that the float has the right numbers or the right precision and so on, so it caused like rounding error, so people would end up in the wrong places and all that. Is that kind of the gist of it?
Yeah. So for example, on okay, so let's go through the different levels. On um, on like one compiler versus another compiler, it might do the operations in a different order. For example, try to come up with an example on the fly. You might do x equals u times v. This is a really contrived example, but it should give you the idea, u times t. And one compiler might compile that as like, mul add. And so, multiply and multiply and then add the two results together. Another compiler might, flat out do the algebraic thing, and it might be like, okay, x equals u times v plus t, and that will turn into, an add and then a multiply. And you can imagine, because you have a limited amount of precision in these floating point values, the result of this calculation could change depending on what the input values are. You could get something different out the other end. So does that make sense so far?
Mm-hmm.
So that's the major one, is what the compiler is doing. Then there's the CPU floating point mode. So the floating point units on a CPU. Okay, well, first of all, you could get compiled to x87, which is like the old school float instructions, or you could get compiled to SSE, because even though you're reasonably familiar with.
Mm-mm.
Sorry?
I'm saying no before you even start saying what you're about to say.
You're reasonably familiar with what SIMD means, aren't you?
No, other than it's the project that never compiles when I run the engine because...
yeah, well, we didn't end up using it.
Yeah, no, I actually have no idea. I have no idea what SIMD is.
Ah, well, let's rat hole even further on this one, because that's fun.
My quest to not do any math today is going swimmingly well.
Just keep asking questions and we'll never get there. So SIMD stands for single instruction multiple data. And so if you have like a multiply instruction, that's going to take, instead of being like a standard x87 multiply will be like x times y, or I'll call it x1 times x2. Whereas a SIMD multiply would be like multiply x1 times x2 and multiply y1 times y2 and multiply z1 times z2 and multiply w1 times w2, and so you can see that it's doing 4 times as much data, and this is obviously that you can get wider ones and such. But
this is kind of reminds me of the whole GPU thing about lining things up and then applying the same.
It's very similar.
Same thing. Okay, so it's like a compiler optimization. I know that you were going to use that, you were going to interop into C++ or C, I guess, to make some kind of adjustment to the game to make it run faster. Why is C# stuck on the first one if you can't do that kind of thing?
Well, there's two things. So to finish the point I was making is you can still, like, a compiler, depending on what it does, can still use the SSE instructions to do floating point maths, and there's let's bring up Intel Intrinsics Guide. So now we're really having some fun here. Let's turn on SSE 1 and 2. And so these are like literally the instructions. So if I wanted a multiply instruction, there's mmmol ps. So this is packed single precision floating point. So this is what I was looking for before. Yes. This is probably wrong, but whatever. So this is the multiply instruction. So you can see it actually tells you exactly what it does. It's like, okay, from 0 to 3, so for 4 lanes, so this is your X, Y, Z, W, take 32 bits from A and multiply them by 32 bits from B, and then do that 4 times. And obviously it does this all in parallel. And so obviously if you're doing 4 multiply operations in parallel, you can, if all you're doing is multiply operations, for example, you can make things 4 times faster for the same number of CPU cycles and stuff. So this is why we were exploring that as an optimization for River City. It's like, oh well, we can make this 4 times faster if we just do this. So going back to this thing, the thing is, there's also single precision number. So this does kind of the same thing. It ignores the top 3 values, so bits 32 to 127, but it does multiply bits 0 to 31. So it's multiply single precision value. So your multiply instruction could get compiled out to an mmol ss, or mol ss is the assemble instruction, or it could get compiled out to whatever the x87 instruction is, probably mol something. And then if you're using I guess I can't remember what the rules are for SSE. I think they're similar, but you could have various options turned on in the floating point unit. So there's 2 that come to mind are there's flush denormals to 0 is one thing you might have turned on. And whether or not that's turned on, you might get different results. Often games turn this on because otherwise, denormals are actually slower to calculate things for reasons. The other thing you might have turned on is, now this is really stretching the memory. I think there's like Intel CPUs do this, Intel CPUs do this, or at least did this, and AMD CPUs didn't, and that is 80-bit precision intermediates. And it's basically the case that it does all the calculations as 80 bits and then truncates them or rounds them down to, when you're done, down to a 32-bit floating point value, because this is single precision float, it's 32 bits. So you can imagine if you've got all this extra precision, you're going to get different values if you're doing calculations at 80-bit precision rather than doing them at 64-bit precision or 32-bit precision.
Right. Okay. Cool.
Yep.
Right. So then we use fixed point structs for our math.
So yes, we used fixed point to sidestep this problem, so that all of our calculations are deterministic. So we know exactly what they're going to be on every system, and we don't have to mess around trying to set the floating point units to do exactly the same thing, because that's a tricky problem, and then getting the compiler to emit exactly the same code, which is an even harder problem.
Right, but you still pay for that. I mean, it comes at the cost of having to, the math isn't as elegant, obviously, when everything is sort of using those kind of heavy extension methods and so on for multiplying. And
so the maths is harder. We lose performance, not least of all because we can't do integer and floating. Actually, I'm not sure that's actually relevant on a modern. It probably is relevant on a modern CPU. I'd have to look it up. But it used to be the case on older CPUs that you could fire off integer and floating point operations kind of in parallel and get a little bit of parallelism there. I'm not sure. I'm trying to remember exactly what's in a CPU. I mean, I have a working knowledge of, of the CPU stuff, but it's maybe not good enough to explain on the fly.
That's okay. Now I'd rather do math, so I think mission accomplished. No, that's good. Okay, but I guess the point was the drawing code was all in float. Like we used float for the drawing code and everything. It was more just for like in-game state stuff that we were trying to make deterministic. But floats are okay. And
floats. There's nothing wrong with using floats. It's just really hard to get them to do exactly like bit for bit the same thing between different systems.
Right, and we don't necessarily need that. So we especially don't need that if we're just talking about the presentation on the screen. Like you're not going to notice that. It's going to get snapped off at the pixel level anyway. So
one day we might talk about this. So this is what I was looking for, and that is like here's a bunch of diagrams that represent what the CPU does, and the part that I was looking for is like a modern CPU has this scheduler, and it sends instructions to different ports, and the different ports can do different things. So what ends up happening, like just for example, in this CPU, there's 1, 2, 3 integer units and 1, 2, 3 floating point units, and so my guess, without actually having read anything at this case, is that so integer, float. Yeah.
Send like one integer execution unit to port 1 and the other to port 2. If they have P or to port 2, you could do them in parallel.
So the point of this is, yes, you can do integer, floating point in parallel, for example, but you can also do integer in parallel. So I don't think we're actually losing any performance on a modern CPU by doing only integer stuff, because we're still filling up all of the integer ports. So, whoa, hey, that's. You want to change your color scheme? I don't. Thank you. That'll be the screen capture complaining. Let's check if OBS is still going. Okay, so yes, and then one day when we do our little discussion about the internals of floating point, which is quite interesting, we can talk about what a denormal is. Okay, where were we at? We were calculating.
We were about to write all the code for the best guessing of the axis.
Exactly. Okay, so we have the separation amount and the separation axis. So you recall up here we have. I see you're actually way ahead of me, so that's good.
Oh, not really. I'm just messing around.
No, mess around. That's worth doing. So yeah, you recall up here that we have this maths absolute. So we can actually get rid of this absolute check here just by making all of our separation values positive, and then using the axis to do our flip. So you can imagine that rather than trying to keep this one positive or negative, we can just say, well, we know that one's negative, so we'll reverse the direction of the axis. Does that make sense?
Yeah, I mean, yeah. We don't. I mean, we're not there yet. We don't have the absolute, but you're basically telling me I gotta normalize the or get rid of the negative separation here and replace it with where'd that? Oh, that's not here. To unit.
No, because so the unit x there is basically what this axis is here. So all you're doing, because we know that later on we're going to multiply the axis by the amount, so we just move that minus sign from there to the axis. Is how we're going to handle this. Because you recall our pattern is like axis 0 plus separation amount times separation axis. So hopefully you can remember exactly this pattern now. This is putting a point on an axis. So we're going to have a multiply here later. So it won't matter which side which of these two the negative is on.
Mm, mm, uh, right. Except, okay. Well, I'm just gonna leave it then.
So leave that there for now. Hopefully this will make sense. So the reason we don't know what the negative is the code that we're going to write is going to be if separation a. Oh, I've got a spelling error in here. Separation, not separation. So this is what we're doing. So if we started making separation a negative, then you can imagine that then separation amount would become negative, and so we'd start to miss all of our our best our best separation amounts. So what we're going to do, instead of saying separation, instead of doing it exactly as we did here, and then we had instead of doing that, all we're going to do is just take that negative sign and switch it over to the axis.
Yeah, my confusion was how did you negative a vector, but I guess that's one of those operator overloads.
Oh yeah. It's it is going to F12 to that. Okay, so you can see what it does is it literally just negatives the components.
Mm-hmm.
And so we'll do the same thing down here. This one doesn't have a negative on it, so that makes our life nice and easy.
Yeah, but where's the else? I mean, we're not done here, are we? I mean, we have stuff to do.
We're not quite done here. Actually, no, we are done here for that particular section. It doesn't do anything.
Isn't this supposed to be B?
Yes, good catch.
And this won't be negative.
That won't be negative, no.
Okay.
So we haven't done anything yet as such, but we have found the separation axis and the separation amount. So yeah.
Okay. So then then we would trap it at the bottom and do something with it down here.
So outside of our loop, if did intersect, why don't we just straight up draw this thing? So if you recall, the separation amount is how much we'd have to move the rectangle. So let's draw this arrow off the rectangle. Let's make it magenta so I can see it. And this is going to be rectangle.position, and this is going to be rectangle.position plus the separation amount times the separation axis.
Remember the thing.
Sweet.
5F zoom. What's that? Zoom. Zoom. Color.
So in theory, this should be pretty much it. This is our separation. So grab one of these.
I don't know where my game went. Slow computer today. Cool.
Yeah. So that looks like it's working. So, I mean, we could pretty much say we're done here, but why don't we do it? Why don't we finish off completely with the slightly nicer code that we had for doing the circles?
Slightly nicer code we had.
So if you go down to the if circles equals 2 count, so this is the case where we have 2 circles, And you recall we actually draw the separated shapes at the end. So,
Oh, right. Yeah.
so I mean, I think this is literally what we already have, is this magenta arrow. So why don't we grab everything else from here, and we'll copy it up into here and finish this sucker off. Now let me go and look. We have A and B, and I think B is the rectangle. Yes, B is the rectangle. So we'll make B the rectangle in this case. So the circle mass we have. Now we need the mass for the rectangle. So what this is going to be is rectangle radius x times rectangle radius y times 4. Now this times 4, does that make sense to you?
I actually don't remember how we have the radius on the rectangle.
So
we did that.
This is pretty simple. So let's draw it. So we've got our rectangle, and we have a position which is the center, and we have a radius x and a radius y. And you recall that the area of a rectangle is the width times the height. So area equals width times height. So in this case, the width, area equals the width, which is 2 times the radius x, 2 radius x, times the height, which is 2 times the radius. So 2 times, I wasn't doing times symbol, radius y. And so if you multiply all this out, you get 4 radius x, radius y. So the other way to think about it is like, you multiply these two and you get that area. And then, you've got 1, 2, 3, 4 of them. So that's how we do the area of a rectangle. And then, so I have this separation, which is the amount we need to move B. So we already have.
Yeah, I just slopped that out. Oh yeah, that's even better. I just
Oh yeah. So yes, so that's negative that, and then that's quite right. So that should be good. And now we have to draw the shape. So this A is a circle, so that's going to be N is going to be the axis. So we'll stick that in everywhere it needs to go. And the A is a circle, so that's going to be circle position. This is B is going to be rectangle position. Now we need to change this from line batch circle to draw rectangle, and that needs to be radius x, radius y. What have I done wrong here? Half width, half height. Thickness. We need the thickness.
should have a rectangle on our line batcheroo.
We could add one there. That's probably not a bad idea. For the time being, let's just we've got one. And then A is circle position and B is rectangle position. That all looks pretty good. Before we jump in there, these colors are gonna make our life miserable. So I'm just gonna make these magenta and make this one cyan and this one orange. So that draw rectangle, you probably want to magenta that one up as well. I think we're good to go. Shall we run it?
Mm-hmm.
See if this does what we want. Looking good so far.
Actually, can't. I forgot what we were.
So
Oh yeah, because
you're not intersecting.
Yeah,
Hey,
yeah. There we go.
That's
Dark
looking
side of
pretty
the
good.
moon.
So we check the corners. Seems to work in the corners. It seems to work correctly with the mass as well. So if we have like a huge circle, the rectangle's going to move. If we have a tiny circle, the circle's going to move.
Oh, that's pretty cool.
Yeah. So we've got a few minutes left, so we could why don't we try and make it so that when we hit space, this thing actually happens.
Sure.
It's nice cobweb of lines we've got going. So let's basically copy this entire shebang. And we'll scroll up to do separation, and then we'll just so we've got rectangles, we've got circles.
Gonna need all of this at some point, or can we just generalize it to one at one point?
So later on, what I think we will want to do is get rid of the cases for rectangles and circles and just be like for shapes to other shapes and remove that code duplication. While we're in here now, because we are doing both at once after the other two, we're going to actually need to do this stuff later. So we're going to grab out this thing that modifies the rectangles just above the circles comment, and we'll shift that off to the end. And hopefully the circles as well. So let's just go through and just get rid of all the drawing code. Basically find calls to line batch and delete them.
We don't need our if check anymore to check the two. Well, we probably will, because these use.
Oh yeah, well
loops. We'll do that later.
Yeah, I'm just like, we'll actually need to loop through some things at some point. You're quite right.
What's going on?
Yeah, you didn't copy in a brackets, a scope around that, so that's probably why you're having issues. So
I don't need thickness. That's kind of a big hint there.
So I'm just gonna yep, looking good. So we'll need another bracket down here. Oh, good at auto set that up. So for every circle and for every rectangle, now this is where, see, this thing that you do that I tend to not do. This is where this pays off, because you only just have to stick like an I and a J in here. Whereas if this was my code, I'd have to go through every single place where it said rectangle, like, and circle, and be like J J J J J J J J J J J J J J J J, etc. So
Yeah, well, there's a. I mean, I don't know. For all the times that's a benefit, there's the times where I don't know. Sometimes it doesn't help with readability or whatever. But
I'm thinking
it's
you
a
might.
style thing.
I'm thinking you might be onto something. I think it's probably worthwhile.
I just can't not do that anymore. I have to var out everything, or I just can't see what I'm doing.
I'm lacking it. I'm contemplating whether I shall modify my coding style to do that more often. There is this thing here, so we've got another I loop in here, so I'll have to change that index as well. And oh look, because we've done this thing, we only have to change it in like 3 places. We'll call that K. So, yeah, I think you've taught me something today.
Yeah. Okay, I'll take it. 5 years later. No, that's not true. I taught you about ordinal ignore case as opposed to using invariant culture because it's slightly faster.
That's also true.
Micro optimization for the win. Yeah, I write down every time you say something like that, so that's why I know. That's why I know that.
Sweet. Yes. For those of you watching, when we were doing string stuff on River City, I was using I was using invariant culture, and I was like, ordinal ignore case is what you want. It's like,
yes.
So yeah, that's a case of Andrew didn't actually read the documentation. It was like, it sounds like what I wanted to do.
Yeah. Oh, there's a lot of that. There's so many. They have so many things in that base class or BCL thing. It's too much, really.
We have this code. There's no need to type that out. Did you delete that?
I didn't. No, I just didn't want to find it. It's somewhere in the drawing mess.
It's just these 4 lines down it.
There we go. Yeah, I did delete them because they weren't being used at the time. I got overzealous.
No, it was reasonable. Okay, so we have those 4 lines. We just need to figure out, and by figure out I mean copy from over here, because we've done this already. So we don't even have to do anything particularly exciting. Pending rectangle separation for J is going to be A move, B move, axis. So I think we might be done.
Cool.
Let's give it the old try.
That only took I think a couple of months or something. But.
Well, to be fair, really it's only a couple of hours, and first attempt at this is that's not unreasonable. So
boom, I did something dumb here.
Okay, let's pending circles.
Pending circles is 10 and I is 10. Oh, is this K? Or, no, that's not K.
No.
Basically, I'm out of.
Okay.
I've reached the end.
Well, let's look at your loop condition. Circles count. Here we go. Here's one bug. Those subscripts.
I do that every time. Yeah, I did that last time too. All right.
I'm not sure.
That'll help a lot.
Not sure that's the actual bug, but that's a bug.
Oh, axis bases are not being used for anything.
Yes. So this is the thing I was saying before. Is like, eventually we can get rid of these because they're just used for drawing. Which is, it's one of the advantages of this algorithm is that makes these things pretty simple.
How did you get rid of axes?
I didn't. It's still
Oh
there.
yeah.
That
Okay.
one we need. That one we definitely need. So
Yep.
and we have
But we
this
have to fix the allocation thing at some point.
exactly.
Oh,
Okay.
Oh, this is not supposed to be circle count twice.
Yep, that sounds about right. Also, this eye, is that an eye there? That's probably why your eye's going out of range.
I couldn't have made that worse.
This is an interesting thing. I read it a while ago. I'm not sure, I can remember where, but it's like the vast majority of nice, it works. The vast majority of bugs in code are copy paste bugs. It's like you copied something and you pasted it somewhere else, and you didn't change that like I to a J or something, and so it's a bug.
Makes a lot of sense.
So it's
probably-
always worth paying attention when you do that, because that's where a lot of bugs come from. So yeah, and then we can make a whole lot of circles and a whole lot of rectangles. And in theory, if we mash space enough times,
Oops.
they will all separate out. So if this
Bottom
was
one's having trouble, but that's just mass. It's gonna round out eventually.
yes, if this was the problem we were actually solving,
Ooh, rounding issue. No.
no, it's not a rounding issue. It's just an oscillation because it's separating one way and then it's got something on the other side, so it has to separate the other way. So if this was the problem that we were actually solving, we could think about ways to deal with that. But I'm not sure it's worth it because it's not really the problem we're solving. And it doesn't hurt us in any way. You can imagine like if there's a problem I've seen like that's sort of similar to this, and you can sort of see that if you like look at this diagram top down, and that is like room layout. So you can imagine like a game like NetHack or something. Have you ever played NetHack?
Not yet. No.
Do you know what it is?
No. I thought I did, but I don't.
Okay, let's bring up some screenshots.
I thought it was one of those old like that dwarf game, Dwarf Fortress or whatever it's
Oh
called.
yeah, it's like one of the earliest ones. It's not the earliest one, but so you can imagine like okay, so you've got a room, and here's another room, and you've got creatures in the room, and it's like you're a thief, and it's an RPG sort of situation, and so and these are all auto generated, so you have to lay out these rooms somehow. Now this one's a bit different because it like splats them down and like draws hallways between them. But you can imagine like if you had a whole lot of rooms you wanted to lay out, one way you might do that is let's erase that and like just randomly place them, for example, and then maybe we've got some circular rooms as well, and then just do that a whole bunch of times. And so if that was the problem we were solving, it's like, oh cool, we've pushed them all apart, so we've got a contiguous yet nicely laid out series of rooms for like an adventure game or something.
Yeah, it actually kind of looks like art to me in some ways, or like one of those tag clouds or something you'd see in a magazine.
Tag cloud is another good example because it's basically the same problem. It's like if you have a whole lot of shapes, how do you lay them out such that none of them overlap, but they're still like tightly packed together. So if that was the problem we were solving,
you just lay them all down in a way that they made sure that at least they all overlapped with at least one of the other ones, right, or something like that, or maybe 4 or 5.
So you could indeed do it iteratively. So you could be like, we'll place one, and then it's like, oh, we'll place another one, so it like lines up, and we'll place another one, so it lines up. This is in fact This is, in fact, you recall I've closed the window now, but
The sprite packing.
this is exactly the problem that the image writer was solving with the sprite packing. It's like, how do we pack these things closely together? Yeah.
Well, I kind of meant from an artistic point of view, you could like first make sure they all overlap so that you got something nice when you started to separate them all.
Oh yes. So one way you do that is like literally you just place them all at the same position.
Oh, sure. Yeah, that's even better.
And I mean, in fact, what I'm doing now is adding slight randomness to it because I'm not clicking exactly the center. But by adding slight randomness, you're going to get, something interesting happen. And clearly, I was adding randomness on the y-axis. In the x-axis. So if that was the problem we were solving,
We'd be happy with what we have here.
Well, what we have here is not terrible, but what we'd then go and do is we'd probably take this bit of code here that just adds up the amount that we want to separate by, and just do something a little bit more sophisticated to try and improve that situation. So, for example, it's like, for example, I'd have to think about it a bit because it's actually this is actually turns what is a relatively easy problem into a kind of harder problem. So people do things, for example, with springs, for example, and they attach. Where's my drawing? So they do we may in fact go into springs because we might want to do this ourselves for something slightly different. But they have a bunch of shapes like this, and they're not quite separated, or in fact maybe they are separated, and it's like, well, we want to bring this one closer together. So what they do is like, all right, we'll put a physics simulated spring between these two, and a spring between these two, and a spring here, and a spring here, and here, and here, and here, and here, and so on. And we'll simulate these springs through, and you can imagine like what will happen with all these springs is like these ones will push apart and these ones will pull together, and we'll iterate over this, and we'll probably still do something like the separating axis test to separate them if they collide, or to sort of towards the end to make sure none of them are touching. None of them are overlapping. But this is sort of the other component of that kind of situation is you use springs to push or pull them apart to make sure they're all positioned sort of nicely, rather than doing that like oscillating thing. So yes, that's what we're doing. So speaking of springs, what we might do, now we have this working, there's sort of two things we want to think about doing. One of them might be to replace this struct rectangle with something along the lines of like struct shape. And we'll talk about how you can do that and why that's useful. And the other thing
that'll be good, because I think I tried to do that prematurely before we got into the details, and it's good to see how you would actually do that. Now that we also know about structive arrays and so on, it'd be interesting to design it.
That's probably where we'll go with that then. Yes, because this is kind of like how I would do it. It's like, all right, I've done circles, and we separate them, and it's like this. It's like, oh, we need rectangles. Let's add rectangles. And then once I have rectangles and circles, it's like, okay, now I'm in a position where it's like, I've got all this duplicate code, and I've got to do rectangles and circles and rectangles and circles. And it's like, okay, this is starting to get ugly. and I would be concerned, and certainly in this case rightly so, that what happens when I need a triangle, because then I have to add, what's that, 9 no, yeah, 6, I don't know, do I have to add like 3 more cases to this, or is it 6 more cases? I'd have to think about it. But I'd have to start getting a whole lot of these, like rectangle versus triangle, circle versus triangle, triangle versus triangle. So yeah, another 3 cases, and I'm like, all right, that's not code I want to be writing. So I do exactly that, and then
Right.
and that's the nice thing about the separating axis thing is we just need to know the axes and I guess the corners, and once we know those, we'll have to do some special case stuff for circles, but it's not that hairy. Once we have those, we can do the thing. We can combine all that code. So we'll do that first. That's probably the interesting programming thing. Then what we might do next after that is springs. So if you've ever played with Box 2D or something, one of these physics engines. In fact, I know that you played with Box 2D.
Yeah, I remember. Try not to remember, but yeah, that Farseer was the Box 2D implementation. That was the du jour one on XNA for a while.
So exactly. That's basically a C# port of Box 2D. It used to be its own physics engine, and then they're like, yeah, it's not as good as Box 2D, so we'll just port Box 2D, which was smart. But what they do in like the demos and stuff, because it just makes life easy, is like, all right, you have a rectangle. I'm gonna grab this rectangle, with my mouse cursor, and I'm gonna click and I'm gonna drag it out like here, and it makes a spring temporarily, and it tries to pull this towards your mouse cursor, and like we were talking about over here, one of the reasons it does this rather than dragging it directly is so that if you hit some other shape over here, it's going to react in a nice physical way, rather than sort of just trying to clip through and then like having this like pop out here because it's separated or something awful like that. It's going to do something a bit nicer. So after we combine them, and in fact, one reason we want to combine them is so that we can have like the one code path doing, we don't want 2 different code paths to do the same thing for a circle. So we'll combine the code paths, and then we'll look at springs, and obviously once we have a spring, this, like to move this thing, we're going to need a velocity. So once we add a velocity, we can start doing some physics simulation as well. So that's sort of the direction we want to go.
I can't wait to misuse the term D'Alembert's law again, because it's the only thing I grasped about combining forces on an object. I'm gonna be.
I'll have to Google that one because I've actually never heard of it.
Oh, that's just. I think it's this very simple thing where you like apply, like friction here and force from this other thing, and you throw them together. It's just a property that they kind of all work like different forces, and then you end up getting the response force that is the one that would make sense. I have that totally wrong, but it's like the one.
Okay.
It's my cocktail party phrase that I can toss out whenever I want to feel confident.
Nice. All right.
So look forward to using that term.
Well, yes. You'll have to tell me what it means.
I'll have to remember again, but I think I got it.
Okay. Let's wrap it up. Thanks for watching, YouTube. We'll see you next time.